Right. Today we are going to discuss the second session of the uh, probability distribution, probability, not distribution, probability. In the last class, we discussed the basic, the foundation of probability, how to calculate probability. Now we move to the second session, that is probability for decision making. Here we will discuss some of the foundational concepts and logic behind probability and how we prepare for the exams. This kind of some tricks. Here you can see two type of diagrams. This is called tree diagram, and this is Venn diagram. These two techniques commonly used when understanding the probability. Right? Let's see. Right. The language of uncertainty. So uncertainty. Probability is measured to probability is a measure to probability is a technique or is kind of scale to measure the uncertainty, and it has two critical distinctions. First one, mutually exclusive, and the second thing is independent. What is mutually exclusive and what is independent? We have to very carefully understand these concepts behind the probability. Without knowing these two distinctive critical things, it's nearly impossible to understand the probability. Mutually exclusive mean, say, when you toss a coin, at a time, right? At a time, you can get head or tail. You can get head or tail. If you get head, you can't get tail. If you get tail, you can't get head. So that is why out of two outcomes, you can get only one. In the same way, if you throw a 6-face die, there are 6 faces, there are 6 possible outcomes, but in an experiment, you can get only one outcome. In one trial, you're able to get only one outcome. That is called mutually exclusive. Events where not more than one, right? Not more than one can occur in a single trial. So throwing a 6-face die is a single trial. The possible outcomes 1 to 6, 1, 2, 3, 4, 5, 6. But at a time you can get only one outcome. If I roll a 6 dice, I cannot simultaneously roll a, right? If I get 1, I can't get 2 or 3 or 4, 5 or 6. If I get 5, I can't get 1 or 2 or 3 or 6, 4 or 6, right? So at a time only one outcome. That is mutually exclusive. Independent, right? Independent. When you toss a coin, at the first, right? First you get head. First time you get head. And second, you toss a coin, same coin, the result may be head or tail. The thing is, the outcome of second trial is independent from its previous trial, its previous outcome. It has no memory. You see, right? When you toss a coin, the chain, right? Event with no memory, right? Any event with no memory called what? Independent event. A coin has no memory. The first toss does not magnetize or change the second toss. They are independent. The first toss, you got head. And does it impact on the second toss outcome? No. Right? No. Likewise, when you throw a 6-face die, the first you got 2, the outcome 2. The second, when you throw your die the second time, the outcome may be any value out of those 6 outcomes. And when you throw the same die for the third time, also the result, the outcome is independent from its previous outcome. The occurrence of one event, independence mean what? The occurrence of one event does not change the probability of another. Getting 2 on toss 1 does not affect getting 4 on toss 2. So the sequence here, first toss you may get head or tail. The second toss you may get head or tail, or head. In the first instance you may get head tail, and the second toss you may get head or tail. No matter, right? This outcome, the previous outcome does not impact the next outcome, succeeding outcome. Probability is the method quantifying these future outcomes. So the mutual exclusive, independent. Keep in mind, these are not two separate. It's not opposite things. Mutual exclusive and independent are not opposite things. Independent, right? The opposite thing is dependent. Dependent. For example, when you take something, right? A toss. When you toss a coin the first time, head. Does the outcome impact on the next toss? That is dependent, right? That is dependent. But it never happened, right? It never happened. So first toss and second toss, there's no connection. There's no relation. The first toss does not impact on the next toss outcome. So that is independent. If it is affect some other cases, if you choose something, right, in the cricket match, you can see the knockout match. First outcome may impact on next outcome. So a knockout match, you can see like this kind of thing. Mutually exclusive. At a time, you can get right getting one outcome, right? You can get at a time you can get more than one outcome. Non-mutual exclusive. Now, based on that mutual exclusive and independent of trials, there are two main laws. First one, addition law. Addition means what? The plus. The addition law. When events are mutually exclusive, we can apply this addition law when the events are mutually exclusive. Here, probability of A or B. Here, you can see the word we use O, and we have to apply the addition law. For example, rolling a die, 6-face die, event A, we define event A is getting score 2. What's the probability? What's the probability of getting 2? You know that there are 6 outcomes. 1, 2, 3, 4, 5, 6 outcomes. We define event A getting score 2. Event B getting a score value 4, score 4. This. What's the probability? 1/6. Probability of getting 2, 1/6. And event C getting 6, 1/6. The question, what's the probability of getting 2 or 4 or 6? In a trial, right? In a single trial, someone asking that what is the probability of getting 2 or 4 or 6? Then you can get the winning, right? If you get score 2, you are winning. When you get score 4, you are winning. When you score 6, you are winning. So what is your winning chance? What is your winning chance? So that time we have to use addition law. Addition law. Here calculation. Here 2, 4, 6. These are the probabilities. Probability. Then altogether we get 3 over 6. Then we have 50% chance of getting 2 or 4 or 6. In other words, we can say the probability of getting even numbers, probability of getting even numbers in a single try of throwing a 6-face die. So in these instances, we have to apply addition law. And also the mutual exclusive, right? And the mutual exclusive events can be expressed in the Venn diagram like this. Even D, right? Even D, even B. These are not connected. Once you get even A, you can't get even B. When you get even B, you can't get even A. That is what mutually exclusive event. So that time, when we visualize this event in the Venn diagram like this, you can observe that clearly there is no intersections. There is no intersection, no overlap. Here you can see the empty space, there is space, no interconnection, right? So this is how we uh, visualize in the Venn diagram. The law here, the probability, right? When we apply the addition law, probability A union B. When we apply O, right? O, the term O, probability of A union B equal probability of A, probability of B. Then it's equal to what? Union of A union B. Right. Here there are two, right? There are two. So we have discussed one, that is O, the selection O, the sequence and. Now we will apply and. Here multiplication law. Multiplication law. When events are independent. When events are independent. In that instances, we use the term and. The probability of getting probability of A and B. Probability of A and B. So that instances we can apply multiplication. The thing is here, not one trial, a sequence of trials. For example, in the first trial, toss one coin, and toss coin 2. Toss, first toss and second toss, or coin 1, coin 2. These two events are independent, right? You have two coins in your hand. Either you can toss those two coins at once. Then the first coin, maybe you get head or tail. The second coin, you may get head or tail. So what are the outcomes? What are the outcomes you may get? Yeah, these are the sample space. Visualizing the sequence. This is the first coin. Toss 1, right? Toss 1. You can get outcome. If in the first toss, you can get head or tail. So what is the probability of getting head? 1 over 2. What's the probability of getting tail? 1 over 2. So this is toss 1. Toss 1. And these are the outcomes. This is toss 2. You see the toss 2. The outcome. Right? Once you get hit in the first toss, in the second toss, you may get head or tail. So what's the probability of getting head or tail here? Probability of obtaining head 1 over 2 and probability of getting tail 1 over 2. Or another possibility, in the first toss, in the first coin, you may get tail. The second toss, it does not impact on the next outcome, next toss, because it's an independent event. The first outcome tail, and the second outcome head. Probability is 1 over 2. Same way, toss, in the second toss, we get tail 1 over 2. The question is, what is the probability of getting head in the first toss and head in the second toss? Which means we get head, comma head. What's the probability? Very simple. We have to apply multiplication rule. We have to apply multiplication rule here. 1 over 2, here 1 over 2, here 1 over 4. So probability of getting two heads. Probability of getting two heads 1 over 4. And probability of getting in the first trial we get head, and second trial we get tail. What's the probability? 1 over 2 into 1 over 2, we'll get 1 over 4. Likewise, in the first toss we got tail, and the second toss we get head, also 1 over 4. And first toss tail, and the second toss tail, probability 1 over 4. You see, there are four outcomes. When you toss two coins, or when you toss one coin two times, there are four possible outcomes. First one, head comma head. Second outcome, head comma tail. The third outcome, tail comma head. Fourth outcome, tail comma tail. So there are four. Out of these four, 1 over 4 chances, 1 over 4, 1 over 4, 1 over 4. So you see the total equal to 1. This is the rule number 1. Probability, sum of all probabilities equal to 1 in a single trial. So add down, total equal to 1. So this is what? Sequence. First, right? Sequence. A toss 1 getting a head. What's the chance? 1 over 2. The second toss 2 getting head. The chance 1 over 4. Then the question is, what is the probability when getting head in the first toss and getting head in the second toss? It means head comma head. What's the probability? We know that probability of this head is 1 over 2 and probability of this head is 1 over 2. So therefore it's 1 over 4. Same thing we are found here. Right? So you see the term, and earlier we used the term O. Right? The O we use for mutual exclusive, and for that we use plus addition rule. And in the independent event, we use and we apply multiplication. Those are the two things. Yeah, the big two questions. What is the goal? You have to understand when we have to apply AND function, or when we apply O functions. So we have to apply the AND notation when it's based on the sequence. Sequence mean like this tree diagram. And the selection mean something in the basket. You have to choose one. So red or black, red or green. like that. So that time you may use O. Now let's see, when we toss three coins, when we toss a three coin, or we toss one coin three times, what will happen? Here, this is toss one. Toss one. What are the outcomes? Head or tail. Head or tail. And the second toss, toss two. What are the outcomes? Head or tail. Once you get a head in the first toss, and the second toss you may get head or tail if the first outcome, first toss is tail. So there are four outcomes. There are possible four possible outcomes. And the toss three, what are the outcomes? Here in the first, right, in the preceding HH, head. Now the chance of getting head. What is that? Head. Is this? And in the first toss head, second toss head, third toss tail. Then head, tail. The first toss head, second toss tail, third toss head, tail, head. Likewise, head, tail, tail. We know that probability. So here, for this outcome, 1 over 2. For this outcome, 1 over 2. And this outcome, 1 over 2. Also 1 over 2. Because these are equally likely events. Now, right now, when a coin tossed three times, or three coins tossed at once, so these are the expected possible outcome, right? All in a right in those three tosses, we get all outcomes exactly three heads. Here, two extremes. When we toss three coins, we can get exactly three tails. So what's the probability of this thing? What's the probability of this? Easy to calculate the probability. Here it's a sequence. First toss, second toss, third toss. It's a sequence. And so that we can apply multiplication rule. Because why? First toss tail and tail and tail. Right? Tail. So here 1 over 2 into 1 over 2 into 1 over 2. The probability is 1 over 8. 1 over 2, 1 over 2, 1 over 2. Here 1, 2, 4, 4, 6, 8. 1 over 8. Likewise, the probability of getting head. We know that probability 1 over 2, 1 over 2, and 1 over 2. Here also 1 over 8. So all possible outcomes here, probability equal 1 over 8, 1 over 8, 1 over 8. 1, 2, 3, 4, 5, 6, 7, 8 outcomes. So total probability equal to 1. Now the question, what's the probability of getting at least two heads? You see, what is the probability of getting at least two heads? So what are the outcomes we can consider? What are the outcomes we can consider? Probability of getting at least at least two heads. At least two heads. Here, at least we are getting at least two heads, so we can consider here at least two heads, head, right? Two heads. Then we can't consider this because we have only one head. Here we have two heads, and we can't consider this, and we can't consider because no heads. So 1, 2, 3, and 4. 2 heads, right? 2 heads. There are 4 outcomes. So we know the probability of this 1 over 8. This is 1 over 8, and this is 1 over 8, and this is 1 over 8. We know the probability. Then the thing is what? This is here what? They are using an AND or O. Here you have to apply O. What is that? Why is that? We have to add. The condition is what? The condition is when we win in the trial, at least 2 heads. The coin tosses 3 times. We will win if we are getting at least 2 heads. Out of 8 outcomes, we have possible outcomes are this and this, this and this. Here, or so we will win if we get 3 heads. We win head, head, head. We win, and we win head, head, tail. So what's the probability of this? 1 over 8. We will win. Here also we win 1 over 8. Here also we win plus 1 over 8. And also here also we win 1 over 8. So what's the probability? Say plus, no? Plus. So all denominator are same. 8. 1, 2, 3, 4. Then 1 over 2. So probability, what's the winning chance? A winning chance is 1 over 2. Here we apply, at the same time, we apply multiplication and addition rule. First we apply multiplication. Why? These events are independent events. Right? Toss 1 independent from toss 2, and this is toss 3. These 3 are independent. But here the chance, right? The logic. What's the logic here? To win the trial, we should get at least 2 heads, right? So my dear students, I will ask one question. What is my, so right, I win only if I get at least, right, at exactly 3 heads. I will win in the game if I get exactly 3 hits. What is my winning chance? What's my winning
1
chance?
over 8.
Very good. 1 over 8. Because our winning chance is limited to here. Head. Right. So what is the winning chance of getting 3 tails? 3 tails on these 3 tosses.
1 over 8.
1 over 8. Very good. Right. Now it's little flexible. The game become little flexible. What is my winning chance when I get at least 1 head in the 3 toss? If I get at least 1 head, I'm winning the game. So what's the probability? Here we win or not? Here in this event, win or not? Here win. Here win because at least 1 head. Here at least 1 head. Win. 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 And here only I'm fail. Here, tell me the probability of winning the game. So I win.
7 over 8.
Very good. 7 over 8. 7 over 8. Right? That's the logic. So 2 tails. So if, right, I will win the game. To win the game, I need to get 2 tails and 1 head. 2 tails and 1 heads. In any manner, in any combination. But in the 3 toss, at least I have to take 2 tails and 1 head. So here 2 tails. For 2 tails, we can here, we lose here, and we lose here, and we win, right? 2 tails, and here also we lost 2 tails here, win, and win, and win. Or here, no, right? At least 2 tails here, so we can't here, right? So that, see, here we win, 2 tails, no, we win here, and we can't win, here win, win. And so here, how many? 1, 2, 3. There are 3 chances. There are three possible out of 8. There are 3 outcomes. We will win the game. Right? So what's the probability? 1 over 8. 1 over 8. Here 1 over 8. So that 1 over 8 plus 1 over 8 plus 1 over 8. Then the probability of getting 2 tails and 1 head is 3 over 8. Is it clear? The point is you should understand when we apply and or there are 2 things, and or, 2 logics, right? At least one, shortcut complements. You might study this complements. Complement one, except, right? Except here the probability of at least one tail in 3 tosses. You see, at least one tail in 3 toes. You see here, at least one tail. Where we can get at least one tail? What's the probability of getting at least one tail? If I win the game, right, I will win the game if I get at least one tail. What's the probability?
7 over 8.
8.
7 over 8. So how do you calculate? How do you find it? Probability of this. No? Probability of this. Probability of this. Right? Likewise, you accept this, you add all these probabilities. That way we have found. Another way, right? Another way we can find. We know that this is the only possible outcome where we are unable to get at least one head. At least one head. Here, this is the only possible outcome where we are not getting at least one head. At least one tail. At least one tail. So probability of this is 1 over 8. And here probability of this 1 over 8. Here we can get at least one head. If the question is probability of at least one tail, probability of at least one tail, here except this, in all outcomes we get at least one tail. So we know that total of this 1 over 8. The total of this 7 over 8, and probability of this 1 over 8. So what we can do is, you know, the sum of all probabilities equal to 1. Sum of all probabilities equal to 1, and you know that the probability of this 1 over 8. What is this? What is this? All 3 heads. It means no tails. There's no tail. The probability of getting no tails equal 1 over 8. So therefore, the probability of getting at least one tail is what? 1 minus 1 over 8 equal 7 over 8. 7 over 8. It is complement, right? It is complement. So we know the total probability and we deduct the complement. here probability of at least one tail in 3 tosses. You see, the total probability equal 1. And even A, what we don't want here, so these are the outcomes, no? These are the possible outcomes. Out of this, we consider all these. At least one tail, no? Right, all we know, we want all this. So we like this. We have to include all these outcomes. But here, only this outcome we are not considered. So what's the probability? What's the probability? We define this event is A. We define this event A. Event A obtaining 3 heads, obtaining no tail, obtaining there is no tail. So what's the probability of that? 1 over 8. And what is this? All other outcomes. We define them, all these outcomes, A complement. A complement, right? This, if we define this outcome as A and all other outcomes are equal to A complement. Here, probability 1, we define even A is getting exactly 3 heads. It's mean no tail. So that's what we don't want. So the probability of this 1 over 8. Then this is everything else. Everything else. Here it may be head, tail, head, tail, head. All other possible outcome that considers the outcome consists at least one tail. Everything else here simply 1 minus A. This is A now. So we know that probability equal to 1. This is 1 over 8. So simply A complement is 7 over 8. So probability A, right? Probability A 1 minus probability not A. Right here the terms not A. The vector method. Calculate probability of no tails. What's the probability? So what's the outcome here? Probability of getting head. It's mean no tail. So probability is what? 1 over 8. Subtract from 1. It's equal 7 over 8. A little confused like this. So probability of A equal, right? Then 1 minus probability A complement. Now let's see um, the event relation intersection versus union. Here intersection mean there should be here, this is intersection, even A and even B get overlap. This is intersection. When we experience intersection, here we have to apply AND logic. And we write like this: A intersection B. And mean in this area represent A and B. This area A only, this area B only, and this shaded area A and B. That's called what? Intersection. We write like this. And right, and yeah, union. O, right? Union mean what? Combination of all possible outcome. Here even A, even B, here A and B. Union mean considering all. Probability of getting head and tail. Head or tail. Probability of head or tail. When asked what's the probability of getting head or tail, 1%, you know, here head, probability of head, even A, head, tail. because here no overlap. Why is that? It is mutually exclusive event. And very careful, when anybody asks what is the probability of getting a head and tail in a one toss, what's the probability of getting head and tail? What's the probability? In a single toss, we should get head and tail. What's the chance? Probability?
1/4.
Only one coin, one toss. We should get head and tail. Is it possible?
No.
No. That's why it is mutually exclusive, and this area has blank. It's mean here a and head and tail, here the intersection is 0. No intersection. That's why probability 0. If anybody asks, right, what's the probability of getting head or tail when we toss a coin? What's the probability? Head or tail?
1/2.
Head or tail. If you win, right? If you get head, also you win. If you get tail, also you win. So only two outcomes: head or tail, right? Head when you toss a coin, once head or tail. My question is, what's the probability of getting head or tail? Head or tail?
1.
1.
1/4.
Not 1/4. 1. 1. It's union, right? O is union. Yeah. What is the probability of head? 1/2. What's the probability of tail? 1/2. And my question is, what's the probability of obtaining head or tail? When you toss a coin, you toss the coin once. Probability of, so there are two outcomes: head or tail. If you toss, right, toss once, the probability of getting head is 1/2. Probability of getting tail 1/2. Question is head or tail. So all possible outcomes. If you get head, you are win. If you get tail, you are win. Right? Both situation, you are win. So the probability, what is the winning chance in that toss? You are win. Any outcome, you are win. The probability of getting head and tail 0. Probability of getting head or tail is 1. Here, when we apply O, right, O, our winning chance increases. Winning chance increases. When we apply and, the winning chance reduces. Yeah. O, we have to add this area and this area. That is called what? A union B. A union B. That's what here. A union B. Then you should apply O. Right. So likewise, when we throw a die, 6-face die once, what is the probability of getting 2 or 4? 2 or 4. What's the probability?
1.
When you throw a 6-face die once, what's the probability of getting 2 or 4?
1/3.
1/3. Why is that? Here, when you throw a die, if you got score 2, you win. If you got score 4, you win. Then what's the chance of winning? What is your winning chance? Yeah, the probability of getting 2 is 1 over 2. Probability of 1 over 6. The winning chance of getting score 4 is 1 over 6. Then 2 over 6. Then 1 over 3. Right? What is the winning chance of getting in one single throw? In single throw, one die, what's the probability of getting 2 and 4? 2 and 4. What's the probability? Is it possible?
No possible.
No possible. Then what's the probability?
0.
0. Right? The 0. That's the logic behind this. And let's see the general addition theorem. It's become a little complicated. Right? Here, the correcting for the overlap. So now tell me, this is mutual exclusive or non-mutual exclusive, this Venn diagram. Venn diagram shows mutual exclusive or non-mutual exclusive. Mutual exclusive mean here when we toss a coin, the probability of getting A and B equals 0. This means when we draw it, when we draw this, right? We draw like this. Head, tail. Then when I ask you the probability of getting H and tail equal what?
0.
0. Because there's no overlap. When I ask you the probability of getting H or tail, probability is what?
1.
1. Right. So why is become 0? Because here there is no intersection. Here no intersection. If it is intersection, right? So do you agree this is mutually exclusive? Toss one coin, head or tail. This is mutually exclusive or non-mutually exclusive. When you get head, you can't get tail. If you get tail, you can't get head. So it is what? It is mutually exclusive. You see here, mutually exclusive. Event where not more than one can occur in a single trial. If one roll 6, one cannot simultaneously roll 2, right? So you can't get 1 and 2 simultaneously. That is mutually exclusive. In mutually exclusive events, here mutually exclusive event, always we can see a gap, right? Addition rule, when events are mutually exclusive, then we can't see any intersection. Right, this is mutually exclusive. If you got A, no chance of tail. If you get tail, no chance of getting head. Right? So if it is non-mutually exclusive, this look like this. So this area represent end. Here in this H and tail, head and tail equals 0 means there is no intersection because it is mutually exclusive. When you see this kind of Venn diagram, it means there is a intersection, overlap. It means it is non-mutual exclusive. Non-mutual exclusive event. Right? Clear?
Yes, sir.
Yes. So don't confuse mutual exclusive event and independent event. Those two are two different aspects, not opposites. Now, you see, now tell me, this is mutual exclusive or non-mutual exclusive, this Venn diagram.
Non-mutual.
Non-mutual exclusive, because there is an intersection. Therefore, it never be a mutual exclusive event. Now, you see here, probability of A union B. A union B. A union B means it covers all areas. This means probability of A or B. A or B. Then the formula is to find out the probability of A or B, A union B, probability of A plus probability B. But you see here, we have to extract this area, right? We have to extract this intersection area for non-mutual exclusive event. But for mutual exclusive event, we don't want to deduct this. Why is that?
Because we don't have intersection.
Yes, equal to 0. Right? Equal to 0. You see here. Here, the same, right? Probability of A union B equal probability A, probability B. And even if you apply probability of A intersection B, also right. Now, here there is no intersection, so therefore, this value equal to 0. Right? So, the general, the general addition theorem says this is the final formula. Mutual exclusive or non-mutual exclusive, no matter. This is the final formula. If it is mutual exclusive, this part becomes 0. If it is non-mutual exclusive, there is a value, right? So why we deduct this? Why we want to deduct this? So you know now the union A union B cover all area, no? Cover all areas. Then why we need to extract this area? Why? Are there any logic behind this? Because it is counted twice. It is counted twice if we simply add A and B. Say for example, this is 3, this is 3. Then A plus B equal what?
6.
6. But cannot be 6. We can't say 6. You see, there are some intersection. There are some intersection area. There are some intersection area is for example 2. If it is 2. If it is 2, then what's the value here? A, what's the value?
1.
1. What's the value here?
1.
1. Now tell me, 1 plus 2 plus 1 equal what? Equal to whole area? Equal to 4. You already said 6. That's wrong. That is wrong. 3 plus 3 equals 6. That's wrong because that's a common area. This 2, it's right. These 2 counted 2 times. How? Here, originally A alone is 1. Here 2, 3. And here 1 plus 2, 3. But when we remove the duplicate, we can get 4, right? Now it's difficult to understand, right? Anyhow, we will do it by using an example. Right? We use an example to prove this is right. Now, see this, read this question. The formula to find out the probability is used to find the probability of event A or B, A union B happening in math O is represented by union symbol. Right? This is the union symbol. Here, probability A union B is O equal probability of A, probability B minus intersection area, probability intersection B. Here, let us use a dice example, a 6-face dice example scenario. You roll 2 6-face dice, right? There are 2 dice, 6-face dice. You throw it. How many outcomes you can get? How many outcomes? Sample space. When you throw 6 dice, 6-face dice 2 times, like this. No, this is the how many? 1, 2, 3, 4, 5, 6. This is first die. Second, 1, 2, 3, 4, 5, 6. Then what is the outcome? Here 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Likewise, here 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Likewise, here 6, 1, 6, 2, 6, 3, 6, 4, 6, 5. Likewise, how many outcomes you can get?
36.
There are 36 outcomes. Now we define event A. The first die is equal 4. Is 4. Event B, second die 4. Right? So here, when we throw a coin, we may get 4, 1 or right. So here, these are the sample space. Now, this is sample space. Right? So assume that first die is white, second die is black. These are the possible outcomes. 1, 1, 1, 2, 1, 3, like that. Or here 1, 1, 1, 2, 1, 3, 1, 4, or other way around, right? So if you say black first and white second, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. Likewise, 1, 2, 2, 2, 3, 2, 4, 2, like that. Here, even A, they define die is 4, right? The first die is 4. Even B, second die 4. So what are the outcomes here? First, here 4, 1, 4, 2, 4, 3, 4, 5, up to what? Here, this one. First one is what? Black here, this area. So how many outcomes? First 4, First, how many outcomes? 6 outcomes.
6.
6 outcomes. This is event A. This is event A. Now, event B, second die is 4. Second die is 4. So, what are the probabilities here? Here. This is second, no? 1, 4. This is 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 4. Then how many outcomes? Event B?
6.
6 outcomes. Now tell me, what's the probability of A and B? So A or B? Probability of A union B. Probability of A is what? Probability of A. 6 outcomes, no? Or total 36 outcome. Out of 36, A 6 outcome. What's the probability? 1 over 6.
6.
And probability, this one?
1 over 6.
1 over 6. 6 possible ways, and altogether 36 sample space. 1 over 6. So if anybody asks, simply you may add probability of A 1 over 6, probability B 1 over 6. You may simply say equal 2 over 6. Then 1 over 3. If you write the answer, it's wrong. Why? You see, how many here? 36, no? Altogether there are 36 outcomes. Then we count, this is A, and this is B. Now let's count. Let us count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many out of 36? Out of 36. How many outcomes satisfy A and B? How many? 6, 7, 8, 9, 10, 11. Am I right? Am I right? Out of 36 possible outcomes, only 7 outcomes only 11 outcomes satisfy our expectations. Right? A or B. Am I right? The problem is here, we count, right? We count this 2 times. This is what? A intersection B. Are you agree? A intersection B,
Yes.
it represents A intersection B. So therefore, we can write this here. Probability A equal 6, probability B equal 6, probability of A, right, intersection B equal what? How many? 1. Fine. Is it right?
Yes.
Yeah, right. Not actually, it is not a probability. Actually, it's not a probability here. 36 over 6, 36 over 6, and 36 over 6. Probability, right? Probability of A, 6 outcomes out of 36. Probability B, 6 outcomes out of 36. Probability of A intersection B, out of 36, 1 outcomes. Here, according to the formula, right, 6 over 36 plus 6 over 36 minus 1 over 36. You see now 11 over 36. Understood? So that's why
Yes.
in the formula we deduct A intersection B, the overlap. See here, apply the formula. Here outcomes of A 4, 1, 4, 2, like that, 6 outcomes. Outcome B 1, 4, 2, 4. Right. The condition is first 4. Probability A. Probability B second 4. The overlap A intersection B, notice that 4, 4 in both list one outcome. So we have to deduct. Then here. So why do we subtract the overlap? We simply added 6 plus 6. We would count the result 4, 4 twice. Subtracting the intersection once correct the count. So every outcomes is only counted once. Let's see. Let us apply that one. We define A is what we define A 4, 1. First score 4. 4, 1, 4, 2, 4, 3, 4, 4, 4, 6. How many? 1, 2, 3, 4, 5 and 4, 4. And even B, same. 1, 4, 2, 4, 5, right? 5, 4, 6, 4, 5, 4. Not actually 3, 4. Right? 3, 4. Then 4, 4 is here. It's common. It is common. You see now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that here this 4, 4 is common. It's cover even A and it cover even B. The outcome 4, 4 is in both A and B, so it's counted twice. If just add a probability of A, probability of B, right? We put 4, 4 two times. So here 6, 6 and 1. 6 plus 6, 12 minus 1 equal. And outside results are what? The complement A union, sorry, A union B, complement is what? Rest of the items. So this is what? That the complement include this, right? All these things. Now let us apply this theory in one case, the price problem setup. A student has a chance for a mathematics 44% for obtaining the chance for subject maths 44, the stud price for statistics, right? Statistic price 58% of chance, and the chance to win both subject statistics and mathematics 16%, 1016. Find the probability the student receive at least one prize. At least one prize mean what? Probability of getting maths plus probability of receiving for statistics, right? And what? Both, right? Both mean what? Mathematics and statistics. So when we draw this diagram, Venn diagram, Venn diagram is like this. Here now, the maths probability is 44%. And statistic 58%. Winning chance of getting statistics price for statistic 58% and 44% for obtaining for maths. For both 16%. So the question is the probability of getting maths union statistics. Probability of getting maths, right? Probability of getting both. So it covers all area. Then what we can do? The probability of getting maths only. Here 0. Right, 44 minus 0.1628, and here probability of getting statistic only uh, 58 minus 0.18, that is 42, and altogether 0.28, 0.16, 0.42, altogether we can get the probability. You see, probability of getting maths price and statistic price. Here probability of maths 44, probability of statistics 58. So therefore, and deduct the common area, the both subject, probability of getting price for both subject, so intersection area. So that 86%, right? Let's here 28 plus 16 plus 42. What's the probability? 10, 16, 3, 4, 86. And what's the probability of getting no prices? What is the probability of getting no price?
0.14.
0.14 or 14%. Right? Is it clear?
Yes.
Right. This is the summary. The management cheat sheet. Summary, right? CO, right? We apply O, and the condition is mutually exclusive. Very simply, we put this probability A, probability B, right? And there's an overlap. We can see this area. In that time, add and subtract the intersection. So when you see overlap, you can't get overlap in the mutually exclusive events. And right, so if it is independent event, you can just multiply probability of A, probability B, just multiply. And the complement, at least, so a complement mean 1 minus none, right? And one challenge for you, what is the probability of getting exactly 2 heads and 1 tail? What's the probability of getting exactly 2 heads and 1 tail when you toss 1 coin 3 times or 3 coins advance? What's the probability? Here we know that each 1/2 chance, 1/2, 1/2, right? So when we chance, so here you see when we can apply here. This is the question. This is the sample space. Probability of getting at least 2 heads. Probability of getting 2 heads and 1 tail. 2 heads and 1 tail. What's the probability here? 2 head and 1 tail. Here 2 head and 1 tail. 2 head 1 tail. 2 head 1 tail. And so on. Then what's probability is what? 1/8. 1/8. 1/8. Simply 3/8. The answer is what? 3/8. Common exam pitfalls, common mistakes. Identity crisis, confusing, mutually exclusive. This means can't happen together. So with independent, don't influence each other. So students are confused, mutually exclusive and independent events. So those two are not opposite. These are two separate things. Double counting, forgetting to subtract the intersection. This one. So it's a union problem. The impossible sum. The probabilities must sum equal to 1. So your answer cannot 1 over, not more than 1. Managing the future. Probability does not eliminate risk, but it provides logic and manage. So you can apply this probability function in stock market scenarios. Probably. Any questions? Any questions? Is it clear? Today's session?
Yes, sir.
I have already shared these materials with you, so you can go through. Okay, now I stop sharing and stop recording.